Hello! In this video, we are going to prove the following theorem. Suppose R is a partial order on A and B is a subset of A. If B is the smallest element of B, then B is a minimal element of B. And this minimal element is unique. So really, we're trying to prove that if B is the smallest element of B, then B is also a minimal element of B. And in fact, B is the only minimal element of B. Now, before we get into this proof, I would like to mention a few things first. To start, what does it mean for a relation to be a partial order? Well, if you recall, all that means is that our relation is reflexive, transitive, and antisymmetric. And second, what does it mean for B to be a smallest element of B? Well, if you recall, all that means is for every element x in B, we have that B comma x is an element of R. And lastly, what does it mean for B to be a minimal element of B? Well, this could be said in a few ways. The way we're going to put it is we're going to say that it means for every element x in B, if x comma B is an element of R, then x is equal to B. Okay, so now let's get into our proof. Now, let's suppose that we've already declared a partial order R on a set A. And let's suppose that we've already declared a set B where B is a subset of A. So now we want to prove that if B is the smallest element of B, then B is also a minimal element of B, and in fact, the only minimal element of B. So let's suppose that B is the smallest element of B. Let's first prove that B is a minimal element of B. Now, because we want to prove that B is a minimal element of B, we really want to prove this statement. Now, we're trying to prove a statement about every element in B, so give me an arbitrary element in B. I'll call it x. So now, with this arbitrary element x, we want to prove that if x comma b is an element of R, then x is equal to b. So suppose x comma b is an element of R. Now, we know that b is the smallest element of B, which means that this statement is true. And this statement works for every element in B. Well, because x is an element of B, that means that this statement works for x in our proof. So we can take this x and substitute it for the x that we have in our proof. If we do that, we get that b comma x is an element of R. Now, since R is a partial order, that means that R is reflexive, transitive, and antisymmetric. In particular, we have that R is antisymmetric. What does it mean for a relation to be antisymmetric? Well, if you recall, all that means is that if we have any ordered pair in our relation, and the inverse of that ordered pair is also in the relation, so say our two ordered pairs are x comma y and y comma x. If our relation is antisymmetric, then this means that x is equal to y. So in our case, we have x comma b and b comma x, both elements of R. Well, since R is antisymmetric, we can conclude that x is equal to b. So notice what we've done here. We started with an arbitrary element, x, in the set B. And we showed that if x comma b is an element of R, then x is equal to b. Since x was arbitrary, we have that for every element x in B, if x comma b is an element of R, then x is equal to b. So we have proven precisely this statement, which amounts to proving that b is a minimal element of B. So now that we've proven that B is a minimal element of B, now we're going to prove that B is the only minimal element of B. How do we do that? Well, what we can do is we can prove that every minimal element of B is equal to little b. So, since we're proving a statement about every minimal element of B, give me an arbitrary minimal element of B. I'll call it little c. Our whole goal now is to deduce that B and C are equal. But before we get into that, what does it mean for C to be a minimal element of B? Well, it means exactly the same thing that we have here. It's just instead, I'm going to replace everywhere we see a little b with little c. Okay, we're going to start by using the fact that B is the smallest element of B. Again, what that means is that this first statement is true. And this statement works for every element in B. Now, since C is a minimal element of B, clearly we have that C is an element of B. So, since this statement works for every element in B, it must work for C. So we're going to replace X with C. If we do that, we get that B comma C is an element of R. Next, because C is a minimal element of B, that means that this statement is true. And this statement also works for every element in B. Now, since B is the smallest element of B, clearly B is an element of B. So, because this statement works for every element in B, it must work for little b. So we're going to replace X with little b. And if we do that, we get that if B comma C is an element of R, then B is equal to C. But we already know that B comma C is an element of R. So it follows that B is equal to C. And so this completes the proof. And the reason why this completes the proof is because, well, we started out by being given a smallest element in B, namely little b. And from there, we were able to prove that little b is a minimal element of B, and it's in fact the only minimal element of B. Right? In this first paragraph, we were able to prove that B is a minimal element of B, and in this second paragraph, we proved that B is the only minimal element of B. The way we did that is we started out by considering an arbitrary minimal element of B. And we showed that that arbitrary minimal element, little c, is equal to little b. Since c was arbitrary, this means every minimal element of B is equal to little b, and thereby concluding that little b is the only minimal element. So yeah, that's pretty much the idea of how you could prove a theorem like this. So yeah, that's pretty much it for this video.